This section is an introduction to exponential functions, so we'll look a little bit about the characteristics of them graphically and do a couple sample problems with the calculator. So first of all, an exponential function is a function f of x equals a to the x, where a is greater than 0. It's not equal to 1, otherwise it would just be 1 to the x. It's just a constant function. X is any real number. A can't be negative because then you'd have issues with negative numbers to different changing powers. A's got to be positive. So first of all, we have the do you know how to use your calculator section example, and hopefully you do. Plugging numbers into your calculator. Now graphs of exponential functions. Well, the basic exponential function a to the x, where a is greater than 0, not equal to 1, 2 to the x and 4 to the x, here you see them. Any number to the 0 power greater than 0 is going to be 1, so these things always go through the point 0, 1. It's always their y-intercept. At the same time, as x gets more and more positive, they go up more and more steeply, with 4 to the x you see rising even faster than 2 to the x. And as far as when x gets negative, 2 to the negative x is 1 over 2, or 2 to the negative 1 is 1 over 2, 2 to the negative 2 is 1 over 4, and so on. And so they get smaller and smaller, but you never actually get to the y-axis, so this the x-axis. So y equals 0 is a horizontal asymptote that you approach asymptotically. And we can see those same sort of transformations over here. This is the function a times b to the x, and if I change b, you see we get steeper and steeper. Over here, if we make a back towards, well, 1, there we're going through, it's 1 times b to the x. So this is b is our base, whereas in the book it was a. So here we get steeper and steeper. As b gets back towards 1, we get to the constant function. And then as b gets between 0 and 1, now we're decaying. And so the way we see that alternatively is down here if we have a to the negative x. Now, the thing about this is that 2 to the negative x and 4 to the negative x, those decay. And the way you can imagine what's going on here is by, let's take a look at say the function 3/2 to the negative x. So 3/2 to the negative x, this one here, we have some decay, but 3/2 to the negative x is the same as 3/2 to the negative 1, and then that becomes 2/3 to the positive x. So that's another way of looking at it, is that having the negative exponent with a base bigger than 1 is equivalent to having the positive exponent out here with a base between 0 and 1, which explains why here we have decay of 2 to the negative x, 4 to the negative x, and we have decay over here when our base is between 0 and 1. And so we get steeper and steeper that we're decaying faster and faster. Here we're growing faster and faster. So back into the textbook, we have all these properties of exponents again, which you need to be aware of as far as manipulating these functions. Here we see the growth versus the decay, the symmetry about the y-axis. As far as thinking of this now as a parent function, it's important because all the things you've learned about transformations of functions, stretching, shrinking, translating, those letters a, b, h, and k, that all applies here as well. So these basic functions, a to the x, we have 0, 1 is your intercept. We're rising up like this. The domain is all real numbers. The range is all positive numbers. We're always increasing. Here's our horizontal asymptote. It's continuous. And a to the negative x, it's very similar. Of course, now we're decreasing. Same asymptote, same intercept, same domain, same range. So this is what I mentioned about transformations a moment ago. 3 to the x plus 1 is equivalent to 3 to the x, but shifted 1 to the left. This is an h of negative 1. You could think of this as 3 to the x minus negative 1. Here, this is a k value. It's outside the exponential function. 3 to the x minus 2, so we're going down 2. Negative 3 to the x is an a value, so we're reflected about the x-axis. And 3 to the negative x is a b value, so it's within the function, so we're reflected about the y-axis. And that goes back to what we said before about how 2 to the x and 2 to the negative x are reflections. And here you see the associated graphs that go with those transformations. All the same things you learned about other functions and the way they transform. E is a very common base for exponential functions. You see it on a calculator. We'll see in calculus how it ends up being derived and why it comes up so often in natural applications. But just like any other exponential function, it's got the same properties. E is around 2.718, and so you can see we're rising here because it's bigger than 1. It turns out that this particular quantity, as x gets very, very large, you approach a value of e. Another thing we'll be proving in calculus in a year or so. And we use that fact when we do things like, this is the do you know how to use your calculator section? These two. But we use the fact about that expression when we get into compound interest. And so here's some applications. This is a formula for discrete compounding. So for instance, if you're going to compound interest annually or biannually or quarterly or daily, something like that. But as you compound more and more often to the point where you compound continuously, as the number of compoundings per year goes to infinity, you use this quantity that approached e, and we end up with this special formula for continuous compounding, whereas if we have discrete compounding, we have this separate formula. And we'll look at that a little bit later. So a little bit more about in terms of applications. This is balance for compound interest. We have a principal of $9,000. The rate's 2.5%. Compounded annually, so n is 1. What is it in 5 years? So t is 5. And you just plug it into this formula. Same idea here, but this time we're doing quarterly, so n is 4, and continuously, so we use the formula p times e to the RT. Radioactive decay. A lot of isotopes decay with a half-life. They decay radioactively. Strontium apparently has a half-life of 29 years. And so one way to express this is to use a base of a half. We have the initial amount times a base of a half, 1/2 times t divided by that half-life of 29. If you want to find the initial amount, you plugged in 0. Anything to the 0 power is going to be 1, so the initial amount's 10. So here it is, initial amount's 10. If you want to find out what you have after 80 years, just plug in 80 for t. As far as keeping track of what makes sense, we know after 29 years we'll have 5. After 58 years we'll have 2.5. So it makes sense that after 80 years we would have somewhere less than 2.5 but bigger than 1.25 because we haven't gone a full 87 years, which would be 3 half-lives. Same idea in population growth, where here's our base E and now we're growing. Initial amount, plug in 0 for t, you get 20. If you want to find out what the population after 72 hours, plug in 72, and then here's your graph. A couple sample problems now. This is number 46. 46, we have this function here, and we just want to take a look at what's going on graphically and look at asymptotes. Now, before we do that, you can't plug in 0 for x because you'd be dividing by 0 in this little fraction in the exponent, so clearly the y-axis is a vertical asymptote. At the same time, if x gets very, very large, then this exponent becomes very small. And e to a very small number, like approaching 0, becomes e to the 0, which is 1. 1 plus 1 is 2. 8 divided by 2 is 4. So we can imagine that our y value will be approaching 4, because as x gets big, again, exponent gets small, e to a small number approaches 0. E to a small number, e to the 0 approaches 1, and the denominator then becomes close to 2, so the y value is 4. And so taking a look at the equation, here's our equation, and we graph it, we see something like this, where we're near 4. The resolution isn't good enough to see that it's not quite 4, it's just approaching it. Here's our vertical asymptote showing up. Suddenly it's our vertical asymptote. We jump over to here, and we approach 4 again. And we can also see that on the table. So if we go over to our table, I just started at 0, went by 1s, and of course we have an error at 0 because you can't divide by 0 in that exponent. If we start to head this direction, the numbers are getting smaller and approaching 4, and it happens the same on the other side too, except from below. So instead of being above 4, they're below 4, 3.99, 3.999, and so on, just to give you an idea of what's going on there. So we've got those two asymptotes. The vertical asymptote at x equals 0, and the horizontal asymptote at y is equal to 4. And then one more problem here. A lot of this section is on understanding the way the graphs turn and transform using the calculator correctly, and a few applications. So one more application is, again, this compound interest idea. We start with, this is number 54, we start with $1,000, annual interest rate of 6%. What do you have in 10 years using the different types of compounding? And so just to show you kind of a way to put this into the calculator that's convenient, it would be over here, is what I've done is I put the function in, is 1,000 times 1 plus 0.6 over x to the 10x, where x is your numbers of times of compounding. And then I just put the table on second table ask, and that way I can put in different numbers for annual compounding is 1, biannual 2, quarterly 4, monthly 12, daily 365, and you see the different amounts of money. And then over here we have, if you did continuous compounding, it's P times e to the RT, so 1,000 times e to the 0.06 times that time of 10. And of course, the more often you compound, the more money you get until you reach that theoretical limit of continuous compounding.